Welcome to Logistic Functions for Restrained Growth. Our objective for this lesson is to fit a logistic function to a data or to data with restrained growth. So first of all, the key words here are logistic function and restrained growth. Okay? So meaning that data with a growth that is restrained or just limited to a certain maximum value carries a logistic function or is modeled or they are modeled by logistic functions. So let us start with presenting you an example which is given by this table here. Suppose that the population of a new subdivision is growing rapidly. So this population of the subdivision, okay, it's new. So meaning when it's new, it caters a lot of reservations, and the more reservations are being produced, the more houses that would be built. Okay, so in this case, X refers to the month and Y refers to the houses that were being built or the population of the houses in that subdivision. So let's say for the first 2 months you have 103 houses in the subdivision. When after 2 months have passed, there are 117 houses. After 2 more months, now it's the 6th month, then the number of houses was increased up to 132. And then after 2 months again, the number of houses became 148. And after another 2 months, the number of houses became 167. So let us look at the graph of this seemingly projected function. So let's graph them. Let's say I'm going to create my graph for this table, for the function defined by these tabular values. So let me begin by writing my x and y values. So my x values are from units of 2, so they have increments of 2 per grid. Okay, so we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and your x is in months, okay? While our y values are in terms of the number of houses built in the subdivision. So let's start from 100, 100, 200, 300, 400, 500, or let's make it more accurate. Let's say let's make the increment by 50 because it's more accurate by 50. So 50, 100, 150, 200, 250, and so on and so forth. Now let's stop first at 250. So if our x is 2, then our y is 103. So that means that our y would be 203. It's somewhere here, right? Okay, when our x is 4, then it's 117. The number of houses built is 117. Okay, now after another 2 months, our x is 6 and our y becomes 132. And then after another 2 months, it became 150. Okay? So are we still accurate with our graphing? So 117, let's say it's here. and then 132. This is here, and then 148, and then 147. So let's say this is here. Okay. And 0, let's say it is somewhere like 100, from 100. Okay. So let us now see the pattern of this graph. The tables have points which, when plotted, creates a somewhat increasingly and concave up. Okay, it's concave up and increasing function. Okay, so this function is an exponential function. Well, at first look, it seemed to be an exponential function, but look that this is a new subdivision. Okay, and a subdivision is always at a certain time. Let's say in 2 years or in 3 years, this subdivision, this area of land in the subdivision will be filled with houses such that you can no longer build a new house in there. So let us say for a certain amount of time, the pattern that this x values project is somewhat exponential. Okay? But at a certain time, you would know, and in reality, we would know that a subdivision will be filled with houses such that the growth of the population of houses will be restrained. So that is how logistic functions are modeled when restraint to a certain number of data, to a certain data is implemented. As in this case, let us say that the number of houses, the population of houses, will finally stop when the number of houses is 100. So let us set a restraint, okay, at this point. Okay, that is our restraint. And this is the seemingly exponential function projected by the table here on the right. But at a certain point, let's say midway of this seemingly exponential function, this will tend to climb, to inflect. Okay? So this will tend to inflect to a certain direction that, you know, this will now go there. It will level off. Okay? So that means it is leveling off. Okay? So that is an illustration of how restrained growth is achieved. Okay? So let us go to the elements and characteristics of the logistic function. A logistic function consists of, first, the point of inflection. The point of inflection normally is being taken or behaved. So it behaves normally in the middle of the graph. So our point of inflection is somewhere here. So this is our point of inflection. This point. The point where, you know, the behavior of the graph suddenly changes from this point or from this behavior going to there. So at this point you could see that the graph behaves concave up, right? So it is concave up at this behavior, at this point. Okay? What else? It is increasing. So the increase is speedy. It is increasing at a higher rate, okay? At a higher rate. Okay. Now, after this point of inflection, this is our point of inflection. Notice that your graph is slowly, well, it is still increasing here, but slowly, right? And it tends to be concave. It tends to go concave down. So it increases at a slower rate until it levels off. So the function now is leveling off at this point, and this is the actual function. Okay, this is the actual function. This is the point of restraint at this point, and this is what we call the asymptote. Okay, this is the asymptote. And the graph is concave down at this point. So it's concave down. So these are the characteristics or the elements of the logistic function. And this function here, the broken line, defines the exponential function. It behaves like exponential function, but because of a certain restraint, it levels off with this point of inflection and then stops to a point that approaches the asymptote. Okay? So this is the representation of our logistic function. Let us picture it in a clearer view. Now the illustration that you see is similar to the previous slide, but this one is a little bit clearer. So as you can see, this is the whole logistic function. You could actually see that in this portion of the graph, it tends to behave like an exponential function until here. Well, an exponential function, to remind you, is a function that increases exponentially, meaning to a certain degree, to a certain radical amount, okay, up to a certain given value for x. Now this logistic function seems to behave like an exponential function up to a certain point called the point of inflection. This is our point of inflection. Now this exponential behavior, once it reaches the point of inflection, will now be subjected to a behavior which starts on achieving the concavity of a downward position, and then afterwards it levels off at a certain restraint. Okay? So this restraint that we are talking about is what we call the asymptote. So this is our asymptote. Okay? Let's say your asymptote is y is equal to c, a certain constant. C, or arbitrary constant. It could be y is equal to 3, it could be y is equal to 4, it could be y is equal to 5, 100, depending on the restraint posited for your function. This point of inflection actually is in the middle of your logistic function. That's why the value of y in this case is c over 2. What do you mean by c over 2? C over 2 is from here to here, from 0 to c. Now just take the average of that value for y from this point and from that point, and that's where the point of inflection is. For example, if our, well, we begin, the logistic function begins at x is equal to 0, y is equal to 0. And let's say it ends at x is equal to 0 and y is equal to 4. So that's the restraint for the range of our logistic function. Then the point of inflection, so to speak, will be found by getting the average of, or the midpoint. Let's say the midpoint or the average in the statistical manner, it's the average, but in algebraic manner, it is the midpoint. So what is the midpoint of these 2 points? The midpoint would be, that would be equal to, for the x, it stays to 0, and for y, we have 0 plus 4 divided by 2. So y is equal to 2. Therefore, the point of inflection, our pi, will be located at the point 0, 2. So this point, if this is 4, will be 0, 2. Why is the point of inflection very important in the logistic function? Because that is the point wherein the behavior of your graph from a certain logarithmic, or rather from a certain exponential behavior, it now tends to create its own distinct behavior for the logistic function. It tends to be concave down, and then afterwards it levels off. Okay? So take note that this is our point of inflection, and below the graph this is concave up. Okay, below this point of inflection, our exponential function, or the behavior of our graph, is an exponential behavior, and it is concave up. While on halfway up the point of inflection, the behavior of the graph has a concavity downwards. Okay, so that is the more distinct and specific elements of our logistic function.